All right, everybody. So this is section 5.7, inverse and radical functions. So a lot of this section will pull together things that we've done previously. So in short, inverse functions undo each other, right? Like we've had some work with these before. It's not possible to find the inverse of most polynomial functions, but some basic functions do have inverses that we can find. Such functions are called invertible. And so recall from a previous kind of section that two functions, f and g, are inverses of one another if for all x in the domain of both functions, we have g of f of x is equal to f of g of x is equal to x. And that just means that both compositions equal x. And let's make a note of that here. Both compositions equal simply x. Okay, and that's how to verify if two functions are inverse. So this how-to explains, again, just as a review, given a polynomial function, find the inverse. And so this is where we'll swap the x's and y's, etc. And so again, that's something that we've done plenty of times. But in this first example, we're going to verify that these two functions are in fact inverses. And so for the first one, we'll go ahead and investigate f of -1, read f inverse of x. And that'll be our first composition. And so this is the first function. The shell is the function f, and then we're just going to plug in this function and then just simplify and see what we get. Hopefully we get x. So this just ends up as 1 over x. And then to divide functions, you multiply by their reciprocal, and then we'll just end up with x. And so that is part one. And then we also need to check in the other direction because it is required that we check both of these. So it's f inverse of f of x. And so now this will be our shell, -1, and then we're going to place this function inside. And so we're just going to verify this algebraically. So this again, dividing a fraction is just multiplication by its inverse. And so this is -1, so we'll just have x plus 1 minus 1, which is clearly x. So the verification was successful in both directions, and they are inverses because both of these compositions yielded x in the end once they were fully simplified. So now if you want to give that a try, you can pause the video and see how you do. Remember, you need to show both compositions to get credit here. All right, so I'll show the full verification here since that is kind of the question itself. So the first verification will look like this. And so this will be the first one that we do. We'll plug this function in here. And then we'll simplify. So this will be 3x over 3. 3 simplify to x. So the first part is done. And then let's go with the other composition. And so for this one, we're going to plug it in kind of in the opposite way. So the other function will become the one that is composed. And so those 3's should cancel, leaving x plus 5 minus 5, and leaving only x. And so because f of f inverse equals x, which also equals f inverse of f, we can say that f and f inverse are inverses. Okay, and we're all done. So example number 2 is finding the inverse of a cubic function. We know that we can find the inverse of this function without restricting the domain because recall from our toolkit functions, this function is based off of the cubic parent function, which is always 1 to 1, which remember that's a necessary requirement for a function to have an inverse. So we already know that, so we don't need to restrict the domain. So we'll go ahead and start off by writing f of x as y. We'll swap x and y. And then we'll solve for y. So this will be x minus 1 divided by 5 equals y cubed. And then just like we would solve from this step if this were a square, and we would take the square root, instead we're going to take the cubed root of both sides. And so we would just be left with x minus 1 over 5 equals y. And we'll rewrite that as in the proper notation. F inverse of x is the cubed root of x minus 1 over 5. All right, so if you want to pause the video and try to find the inverse function of this cubed root function, come back and check your answer. All right, so the inverse function of f should be x cubed minus 4. Right, so moving on to the next section, we'll learn to restrict the domain to find the inverse of a polynomial function. So we know from earlier in this section in chapter 3 that a function must be one-to-one to have an inverse. Thus, sometimes it is necessary that we restrict the domain of a function to make it one-to-one prior to finding its inverse. So remember, we know a function is one-to-one if it is strictly non-decreasing. So we just need to restrict the interval to a place where the function is non-decreasing. And another note that is important, recall that the outputs of the function f do become the inputs of its inverse, which again we denote with this notation, f inverse of x. So we've already talked about this bit about restricting the domain. And so here is your how-to if you'd like to go back and review those steps later if you need to. So finding the inverse function of f. This is example number 3. So notice in A and B, we have exactly the same function, just with different domains, okay? And both of these domains, this part is strictly decreasing. And this one is strictly increasing. And this serves to illustrate that it doesn't really matter which one. It just has to be one or the other, either strictly increasing or decreasing. And we've actually primarily gone with the strictly increasing part just because that's much easier. So let's go ahead and find the inverse function algebraically first. This will kind of work for both because they are the same function. So we'll start by replacing f of x with y, and we'll have x minus 4 squared. We'll ignore the domain for now. We'll swap the x and y variable, and then we'll solve for y. So this would become plus or minus the square root of x equals y minus 4. And then so we would have 4 plus or minus the square root of x equals y. And this is actually going to be our inverse of f, right? So the only thing we need to do is for both A and B, we need to determine, do I choose this positive version, the positive case, or do I choose the negative case? And so in order to do that, we have to recall what I said a second ago, and that is this statement that's highlighted in yellow. Remember that the outputs of the function f become the inputs of its inverse. And so what we have to consider is basically this. So f of x domain must match the inverse's range. So that means that, so dot, 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 f of x the inverse, all of its outputs must be greater than 4, because that is going to make this domain match with this range. And so we know that those have to be interchangeable for the inverse. So in this case, what case, the positive or the negative, would make these outputs all greater than 4 for the inverse function? So that would be if we choose the positive case, because if we're choosing the negative case, then we would not get outputs that are greater than or equal to 4, right? Because we would be subtracting something from 4. And so in this particular scenario, we use the positive case. So the inverse in A is going to be 4 plus the square root of x. And then for this other part of this example, part B, notice the domain is now x less than 4, so the output of the function's case that we choose must be less than or equal to 4, and that's what's going to actually happen if we choose the negative case here, right? And if you're unsure, you can go ahead and plug in some values and see in the domain that's given, what are we going to get? Are we going to get this output that's greater than or equal to 4 here, and x is less than 4, or the outputs are less than 4 in this case? Because what we're going to need to see over here is that all x for the f inverse function, those outputs need to be less than or equal to 4. And so if we're plugging in values of x, the only way that the outputs are going to be less than 4 are if we're subtracting something from 4. And that's how we need to know that we can use, or have to use, the negative case here. Okay. All right, so in example 4, we actually are going to need to restrict the domain ourselves. This is finding the inverse of a quadratic when the restriction is not specified. So remember, in order to find the inverse of a function, we have to restrict the domain to make it 1 to 1. So in order for that to happen, we need to find the interval on which this function is 1 to 1. And in order to do that, we're going to go all the way back and remember that this function is a toolkit function, x squared, that has been shifted down 3 units and to the right 2 units. And so our vertex is going to be, -3, +2. And so this is where our vertex will be. And so from there, remember, if we want the strictly increasing part of the function, then we only want this domain, right, greater than or equal to 2, because we want that to be non-decreasing. And so we will restrict this domain to be x greater than or equal to 2. You could also choose less than or equal to 2. It doesn't really matter. You'll just kind of have to continue with that when you find the inverse. So the next step is to find the inverse. And so we'll rewrite f of x as y. And then we'll actually find the inverse. We'll swap the x's and y's. And then we'll solve for y. So this will be x plus 3 equals y minus 2 squared. We'll take the square root of both sides, giving us a positive and negative square root of x plus 3 equals y minus 2. And so then we'll be able to finish this up by adding 2 to both sides. And so again, we need to consider whether we want the positive or negative case. And so one of the things I'm going to do to make that easier to see is I'm going to rewrite the order here, so I can see whether I'm actually adding or subtracting something from 2. Because if you notice, we're interested in making sure that the outputs of this function are going to be greater than or equal to 2. So remember, we're looking to see, remember this is f inverse, and we need f inverse. Its outputs need to be greater than or equal to 2. And so let's determine which case we will choose. So in order for this output to be positive, we can't subtract anything from 2, right? Because if we need everything coming out of this function to be greater than or equal to 2, if I subtract anything, then that's not going to work. We're going to clearly be less than 2. So the only option for us is to choose the positive case. And so this would have to be 2 plus the square root of x plus 3 for the inverse function. And that would be for the domain of this function. We would have to choose the values such that f of x is greater than or equal to 2. So this is going to be our inverse function. Okay, so if you want to give it a try, sometimes these can be kind of difficult to kind of wrap your brain around until you do several of them. So I encourage you to do that now and try to find the inverse. That they've restricted the domain for you, so all you need to do is find the inverse function. All right, so you should have found that f inverse should be the square root of x minus 1. So from there, now let's talk about solving applications of radical functions. And so this is the steps as a reminder of how to find the inverse of a radical function. And so example 5 asks us to restrict the domain of this function and then find the inverse. And so the domain of this function, remember that we cannot have negative numbers under the square root. And so I need to take what's under the radical and set it greater than or equal to 0 to determine what are the valid parts of the domain here. So what's okay to plug into this function, it'll give us positive numbers under the root, is x is greater than 4. And this is the domain of the function f. And so the next step is to find the inverse. So we restricted the domain, and now we want to find the inverse. So we'll start that process just like we've been doing. Now let's switch the x's and y's and solve for y. So I'm going to square both sides now. And I'll be left with y minus 4. So this would be x squared plus 4 equals y. And so at the end here, remember, we've found f inverse of x. And we've got to remember, and this is super important, along the same line as what we've been doing, the domain, or the inputs of f inverse of x, must be restricted to the range of f. So now we have to go back and find the range of f to make sure that we're doing that. The range of this function is x is greater than or equal to 0, right? You can do that with a sketch, or you can do that using the domain of f, and to see the outputs that come from the domain values. Remember, we found those here. So the lowest value I can plug in is a 4, which would give me the square root of 0. So they're the outputs that are possible are everything 0 and up. And so we have to restrict this particular domain to the range of f. And so the way we do that is we're going to have to dictate that the only thing that can go in here are numbers greater than or equal to 0. And so that takes care of restricting the domain of this function and finding its inverse. And so if you want to go ahead and give number 4 a try, find the inverse of this function, then come on back and check your answer. You should have found here that the inverse is x squared minus 3 divided by 2, where x is greater than or equal to 0. All right, so applications of radical functions. So radical functions are common in a lot of physical models when we use these in the real world. And so example 6 takes this cubic function for a cone shape where the height is equal to twice its radius. And so we're given this formula, right? This is a formula of r in terms of v, right? So this is r. Sorry, I lost my train of thought. This is v in terms of r. All right, because the variable is r. And so we want to find the inverse function that determines the volume v of a cone, and it is a function of the radius r. So then it wants us to use the function to calculate the radius of such a mound of gravel measuring 100 cubic feet. And so the way we're going to do this is we're going to first determine the meaningful domain. And the meaningful domain here, remember the domain is going to be the set of reasonable r values. That's going to be r greater than or equal to 0 because it doesn't make sense to have a negative radius. And then let's also talk about the range as a result. The range is going to be v greater than 0 as a result of, defining that domain. And so this will also be the domain of the inverse function. So let's make that note here. And so in order to find this, we just want to solve for r in terms of v, which is really just solving for r. And so let's do that. All right, so if I start with v equals 2/3 pi r cubed, to get rid of this fraction, I can multiply by its reciprocal, and I'll have 3v over 2 equals pi r cubed. I'll divide both sides by pi, and I'll have 3v over 2 pi equals r cubed. And remember, to resolve that cube, I'm going to take the cubed root, or the third root of the left-hand side, and I'll be left with r. And here is our function r in terms of v. And so this is the inverse, and that is actually r in terms of v. And so remember, it asks us to also calculate the radius of a mound of gravel with a volume of 100 cubic feet. And it wants us to use a value of pi equals 3.14. So that's an approximation. But we'll just plug this into this formula. And so this will be 3 times 100 over 2 pi, which it doesn't want us to use pi. It wants us to use 3.14. So we'll do what it asks. And then we'll just plug all that in our calculator and we'll obtain a value for r. So I'll give you a second to do that while I do that. So that'll be the cubed root of 300 divided by 2 times 3.14. And we'll get that that's approximately 3.6 feet for the radius of a cone constructed in this way with a volume of 100 cubic feet. And so that is one application. So one thing I want to bring to your attention is notice we didn't swap the variables when we found this inverse. And in a real world context, instead of swapping the x and y's per se, we just change which variable is considered the independent variable instead. So the same process, we're just not swapping x and y. So determining the domain of a radical function composed with other functions. Now, this is where your knowledge from chapter 3 is going to come in very, very handy. Because when we take a radical function and compose it with another function, in this case a rational function with an x in the denominator, finding the domain can become a much more complex process. And we've seen this kind of before, but it's showing up again as promised. And so the first key thing we need to understand is there can be no negative numbers under a radical. Not in the real numbers anyway, right? And that's where we're operating right now. And so we need to determine first where all this stuff under the radical is greater than or equal to 0, because that is going to be the first component of the domain of this function. So where, and this is an algebraic equation that's asking this, or an inequality that's saying where is what's under the radical greater than or equal to 0. And so this is interesting because we're going to have to really kind of think about this. And so, what we learned in the last section is that rational functions can behave kind of crazy around their intercepts and especially their asymptotes. And so, step number 1 is what are the x-intercepts, because that's where the sign of the outputs are going to change, number 1, and the vertical asymptotes, because, there's some crazy behavior that could indicate a sign change of the output there as well. And so you'd be able to determine that the x-intercepts occur at x equals -2 and x equals 3. And the vertical asymptotes occur at x equals 1. And so these are the values of interest. And the question we're going to be looking to answer here is what intervals of the domain give us positive outputs for the function f. And one of the easiest ways to do that is I like to draw a number line, right? Because that kind of helps me visualize what's going on. And so here I'll place my vertical asymptote, and then over here would be 3, and over here would be -2, which are my x-intercepts. So I know that there are potentially some things going to be changing at these, special values. And so what you want to do is similar to what we did in class today. That's one of the reasons I introduced the table. So I want you to use a table to investigate the signs of the outputs for this function, right? So you're going to plug that into your table function. I suggest making a step of maybe 0.1 or something very small. And we want to start on the left side of -2. And so let's start at maybe, -2.1. And then we're just going to scroll, right? And you want to pay attention to what the signs of the outputs are around each of these values. So we're going to see that on the left side of -2, everything is negative. As we keep scrolling, there is a 0 at -2. And then after we pass that, moving to the right, everything becomes positive. And then we're going to hit our asymptote value at 1. So you have to scroll for a while to get on up there if you've set your step as small as mine, which I do definitely suggest doing that. You'll get an error at 1 because that's an asymptote. And immediately on the other side, you'll see that the outputs have become negative. And so then we want to continue on scrolling down through until we hit our other intercept at 3. And because it's just a single multiplicity, you know, we expect it to pass on through. And that would mean that these outputs would become positive because we've passed through that axis. So again, if you've lost track of what we're trying to figure out, is what are the intervals that give us outputs for f, specifically, that are positive, right? Because our original question here asked us to locate those. And so that is from here to here and from here to here. And so really what we want to make sure that we capture, rather than really positive, are not negative. And why is that an important distinction? Not negative. And that's important because having a 0 under a radical is fine. And so let's write this domain. So we have -2 all the way to 1. And then we have a break. And then we have from 3, including 3, all the way to infinity. And so these are the values that make non-negative values under the radical in f. Okay, so these are the non-negative outputs. This is the regions of our inputs. And now you have to consider one extra thing, and that's that not only are we looking for negatives under the radical, but we're also looking to restrict where the denominator is going to equal 0, because that also is a domain restriction. So we have to notice that x cannot equal 1. And so what we're going to do is we're going to come down here to our domain that we already located, right down here, and then we're going to make one tiny edit to account for the fact that we have to exclude that 1. And so now that we've taken out that single value that's going to cause us an issue in that denominator, we actually have the appropriate domain for this radical function composed with a rational function. So there's a lot of steps there. You really have to make sense of what you're doing. So finally here we have finding inverses of a rational function, especially in context. And this is actually example 7. I think I messed up numbering. I apologize. Actually, no, that's number 8. Whoops. Okay, so look, that's actually easier to fix. Check it out. So finding the inverse of a rational function. Sometimes this is really useful in a real-world application, especially when this rational function is like a concentration application where we have a ratio of 2 linear functions. And so notice that what we are given is c in terms of n. And I'll give you a second to read this particular scenario. Make sure you read all the words and try to internalize what is actually going on so that we can make sense of this scenario. All right, so we want to find the inverse of the function. We want to find an expression for n in terms of c, which is exactly the opposite of what we started with. And so in order to do that, we're going to do like we did with the volume. We want to solve, instead of r this time, we want to solve for n. And the way we're going to do that is we're going to multiply by the denominator on both sides to eliminate that denominator. That's 20 plus 0.4 n. And so now I'll need to distribute the c. So that'll be 100c plus cn equals 20 plus 0.4 n. And remember, we're trying to isolate n. So I want to get all the n's on one side. So this will be cn minus 0.4 n and 20 minus 100c. And so then I can factor out an n. And finally, I'll divide by c minus 0.4. C minus 0.4. And now, notice I have solved for n in terms of c. And so this is n in terms of c. and that means that we're done. This is the inverse of the function that we were given originally. Inverse. Right? So now it wants us to evaluate and determine how much of the 40% solution should be added so that the final mixture is a 35% solution. So what's important to understand here is what N and C are. And so N is the amount of 40% solution, and 35 is the final actual cumulative percentage of the mixture. And so we'll plug in C equals 0.035. Or 0.35, excuse me. And then it will give us N, the amount of the 40% solution we need to add. So this will be 20 minus 100 times 0.35. And 0.35 minus 0.4. And I'll get that. That should be 300. And so 300 milliliters my dog is going crazy. The 40% solution should be added. Let me double check that. Let me double check and make sure that I did that correctly in my calculation. So this would be 20 minus 100 times 0.35 divided by 0.35 minus 0.4. Yep, it's 300. Okay, I was worried that it might have been 30. I just wanted to double check. Always a good idea. So that is that. And then finally, if you want to give it a try to see if you can find the inverse of this function, I'll give you a second to do that. All right, so that should be the answer you got there. We will be ready to work some problems on the boards when you come in on Wednesday. So make sure that you review the video. I know this is a lot, but that's just the nature of this particular topic. Luckily, if you really did your due diligence in Chapter 3, it should be relatively simple to kind of call some of that back up, but it will take a little bit of effort. So I encourage you to go ahead and take a look at the problem set and make sure that you're working